Okay, so for this video, we're going to be talking about F is equal to Bill. This F is the magnetic force. This is the magnetic field strength, or the magnetic flux density. Or magnetic flux density. I stands for current. And L is length. So let's just put some numbers in. So for example, 1 Newton will be experienced if you have 1 Tesla and if you have 1 amp that is of 1 meter. Or alternatively, if you have 1 Tesla, that means it is 1 Newton per 1 amp per meter. So if you have a field strength of 1 Tesla and the current is 1 amps of 1 meter, let's just draw a diagram. So if this length of wire is 1 meter and the current is 1 amp, the field strength is 1 Tesla. Now it has to be perpendicular for it to work. So if the current is going this way, then supposing it is at right angle, so let's just say the magnetic field is going that way. Right, so assuming that this is the conventional current, the field is going this way, so it would go up. So that would experience 1 Newton up. So this is 1 amp to the left, and this is conventional current. Conventional current. Okay, so 1 amp is to the left. The field is going this way, so the field is coming out of the board. The current. Okay, so the field is this one. That's the field. That's the current. So it's going down, not up, down. All right, so let's just do that again. So the field is coming out of the board. The second finger is the field. And assuming that it is conventional current, so the field is coming out, conventional current is going from left to right, so it's 1 Newton, so the force is going down. All right, so let's just add a few more features. So I'm just going to carry on drawing the field lines. So these are all parallel. So these field lines are, well, they should be parallel. Parallel. What's this? Okay, they should be parallel, okay? I've just drawn it very messy. Okay, so these should all be parallel, okay? So these lines are parallel, magnetic field lines parallel. And this is 1 Tesla, okay? So the field lines are the magnetic field lines of 1 Tesla. The current is 1 amps going to the left, to the right, so left to the right. And it's conventional current. The length is 1 meter, and it would experience a force of 1 Newton downwards. All right, so if we have a current, so this is a wire, and supposing the current is coming out. Now the way I remember it is chow. So C means clockwise if it's going in, and anti-clockwise if it's coming out. Okay, so what I mean is that if the current is coming out, the field lines would look clockwise. And so because it's coming out, that would be anti-clockwise. So if you were to look at head on, anti-clockwise, it would go this way. So that's anti-clockwise. If you look at it from the top. So if you were to look from the top, that means the current is coming out. The magnetic field would be anti-clockwise. Anti-clockwise meaning it's going in this direction. So that means it's coming out. Now if it's going in means, that means in. So if the current is going in this direction, it is going clockwise. So the field line would go clockwise, like on a clock. So on a clock, it's going 1, 2, 3, and so on. So it's like a clock, it's going clockwise. So let's just draw another diagram. So for example, this is a 3D representation. So let's just say the current is going up. If it's going up, supposing you look head down, supposing you at the top, it looks like it's coming out, isn't it? So if it's coming out of the page, it's coming out of the page. Out is anti-clockwise. So your magnetic field lines would go anti-clockwise. If you look from the top, clockwise would be going this way, so it's going this way. So it would be anti-clockwise. All right, so let's draw a wire that's in a magnetic field. So supposing you have a magnetic, sorry, if you have a magnet, so this is a magnet. So this is a magnet, and you have N and S, N here, S there. And supposing that the current is coming out of the page. So the current is coming out of the page. What are the magnetic field lines going to look like? So if you remember CHAO, so CAIO is coming out, so it's anti-clockwise. So it's going this way, right? And it's always by convention, it's always north to south. The field lines is always north to south. So if we draw the field lines going this way, this way, this way, this way, okay? So it's always going from north to south for the magnetic field lines, and the magnetic field lines that of the current coming out is anti-clockwise. It's going, so we can just add, okay, so it's going this way and this way, this way, this way. Now, can you see that the field lines here is going from north to south, but the field lines from the current is going from right to left. So the field lines here is going in this direction, while the field lines from north to south is going in this direction. So that will cancel. So the top part is cancelled out, because the field lines are going from right to left, and the field lines from the magnet are going from left to right. So that will cancel with that, and that will cancel with this. So now that's going to go down, isn't it? What you're going to have overall, at the bottom, these will add up. So these will stay where it is, as in the direction will stay where it is. It will just be doubled. However, the field lines here will cancel. So if I just draw the Y here, so that's the Y coming out. Now, what it would look like, it will look something like this. That's just a rough drawing. So the field lines will look like this. So the direction of the field lines is going in this direction, and then it's also coming out. So because that cancels with this, there's nothing hitting that, assuming that this gets weaker, because the magnetic field lines gets weaker as you get further away from the wire. Now, the magnetic field lines of the magnets are much stronger. So the field lines are going in this direction, going from left to right. And this is going to carry on going in this direction. Okay, so let's try this question. Suppose the current is 5.2 amps. And suppose it's at right angles to the uniform magnetic field. And you know the flux density is equal to 19 milliteslas. 19 milliteslas. So this is a question. And it experiences a force of 1.2 times 10 to the minus 2. So you know that F is equal to 1.2 times 10 to the minus 2 newtons. What is L? Okay, so they will give you the three quantities. If I was 5.2 amps, B was 19 milliteslas, F was 1.2 times 10 to the minus 2 newtons, what is L? So what was the equation? The equation is F is equal to B. So try it on yourself, try it for yourself first and see if you get L. So rearrange for L. So try it for yourself. Right, so L is equal to F divided by BI. This is just simple rearranging the equation and putting the numbers in. So what is L? L is equal to F. So you've got F is 1.2 times 10 to the minus 2. I'm just ignoring the units. And I'm dividing it by B. Now what's milli? Now for these questions, you need to be familiar with these prefixes. So that small m is milli, and milli is 10 to the minus 3. So it's 19 times 10 to the minus 3, and you're multiplying it by 5.2. And what is your answer? So 2, 10 to the minus 2. I'm dividing it by 19 times 10 to the minus 3 and multiplying it by 5.2. And you should get 0.121. Now they've done it in one decimal place, so let's do it to one decimal place. So it's 0.12. 0.12 meters.